When you click start on a cluster, something is happening in the background. It's not instant, there is a sequence. And understanding that sequence tells you a lot about how the whole thing is built. Let me now walk you through it. Step 1. Kubernetes schedules a driver pod. One pod comes up with the CPU and memory you set, running the Spark version you picked. This is the brain of the cluster. Nothing else moves until this is ready. Step 2. Executor pods come up. These are the workers. Based on your setup, multiple worker pods launch alongside the driver. Each one runs a JVM and does the actual data processing. Step 3. Endpoints open up. The data plane exposes 3 connection points. Number 1, a Thrift JDBC endpoint. Number 2, a SparkConnect endpoint. And number 3, an Arrow Flight endpoint. All 3 point to the same cluster. Your SQL editor, your notebook, your BI tool, they all come in through one of these 3 doors. Step 4. The cluster shows as running. From your first query, the driver breaks the work into tasks, sends them to the executor pods. Each pod reads the data it needs from storage, and the results come back through the driver to you. One thing worth knowing here, the executor pods talk directly to your storage layer. The driver is giving out instructions, not moving data itself. This is what keeps things fast, even on very large reads. 3 actions you will use regularly. Number 1, restart. All pods shut down and come back fresh with the same setup. Use this when something feels off or you just want a clean start. Number 2, terminate. All pods are removed and the cluster goes to a stopped state. No compute is running, nothing is being charged for active use. Use this when you are done for a while. Number 3, configure. Apply changes to the cluster. Some changes go live straight away, others need a restart to take effect. Use this for sizing changes, Spark settings, or auto-scaling updates. One thing people get wrong. Terminating a cluster does not touch your data. Your tables, your Pocket files, your iceberg metadata, all of that lives in a storage and is completely safe. You are only stopping the compute layer. Now, auto-scaling. This is how the cluster adjusts to what you need without you stepping in manually. You set a lowest and highest number of executor pods. When there is more work coming in, more pods are added. When things go quiet, pods are removed. If no queries hit the cluster for a set number of minutes, the executors wind all the way down. The driver stays up, only the workers scale up and down. That means your connection stays alive and the next query does not have to start from cold. For most shared analytics clusters, this is the right default. You are paying for actual processing, not for a cluster sitting idle. There is no single cluster size that works for everything. The right setup depends on the shape of your work, not just how big it is. Let me explain what that actually means. 2 things define how a workload behaves. The first is how many people are sending queries at the same time. Many people with small queries like a shared BI dashboard puts a lot of pressure on the driver because it is the one doing the planning for every single request. The second is how much data each query has to move through. One massive ETL job on a training run where you scan the whole table, that puts pressure on the executor pods, not the driver. These 2 things pull in different directions. More users at the same time means you need a bigger driver. Bigger jobs scanning more data means you need bigger or more executor pods. Getting this backwards is the most common sizing mistake. Here is how this maps to real setups. Number 1, ad hoc SQL work. Small to medium driver, 1 to 3 small executor pods, auto-scaling on, idle timeout of 15 to 30 minutes. The cluster winds down between sessions and starts back up quickly when someone runs a query. Number 2, BI dashboards in production. Medium to large driver because many people hit it at once. 4 to 10 medium executors, lightly scaled, kept running during business hours. Dashboard load time is a user experience problem and cold starts during the day are painful. Number 3, daily ETL batch jobs. Medium driver, large executors that scale out for the job, auto-scaling on, terminate after the run finishes. You only pay for the time the job is actually running. Number 4, streaming jobs. Set the size for your busiest expected load from the start. Fixed executor count, no auto-scaling. Streaming jobs need steady throughput and sudden scaling can cause gaps or slowdowns. Number 5, ML training. Large driver, fewer but memory heavy executors, no auto-scaling. Training runs need stable resources from start to finish. Losing an executor halfway through a training run is expensive and sometimes unrecoverable. Number 6, DBT runs. Medium driver, 4 to 8 medium executors with auto-scaling, terminate after the run. Same pattern as a batch job. 3 things to keep in mind as you size your clusters. First, start smaller than you think you need and only go bigger after you can see where the slowdown actually is. Most teams over-provision early and pay for resources they never use. Second, If many small queries are coming in at the same time, make the driver bigger. If one enormous query is the problem, make the executors bigger. Those are two completely different problems with different answers. Third, do not put your most important workloads on the same cluster as exploratory or experimental work. If someone runs a query that crashes the cluster, everything on it goes down. Keeping workloads separate is cheap, incidents are not.